Just let me know. Hello, everybody. Welcome to the first class on the derivative, which we're just going to be covering limits today because obviously we have a shorter class. And basically, limits are, as simply as I can put it, limits are what happens when we get close to an x value, but don't actually touch the x value. We're like, what's happening to the y values as x comes close to something? And if you've seen the videos that Tom has, that'll make sense, hopefully. If not, let's just get to it. So we're going to cover up to about page 13 today. And I'll try to skip as much as I can that I don't think is important. But just, hold on to your butts and, follow me along for the ride. Most of today will be me explaining things and going through examples with you. The following classes have a little bit more practice, exercises, things like that. But because of the nature of today, I'm going to be talking a little bit more than usual. Okay, so first things first, we're going to talk about continuity. So what does it mean for a function? Oops, right away, I got a problem. What does it mean for a function to be continuous? Well, the easiest way I can put this, let's just look over at this function here. A function is continuous, and that's an important concept for later. Function is continuous if no matter where we move along the curve, it doesn't have any weird things happening. Like, it doesn't break. It doesn't have a jump. It doesn't have a hole. It doesn't shoot off to infinity all of a sudden, real steep. Actually, even if it does go to infinity, that's okay. But if you were to use your pencil or your pen and follow along the line, if there's nothing crazy going on, then we know it's continuous. And that's all we really need to know. There's a little way to remember it here. You can draw the graph from negative infinity. So that's all the way over here, as far left as you could possibly go, to positive infinity without ever lifting your pencil. So you can just trace the function and go, yeah, okay, no problem there. No jumps, no holes, no breaks. It's continuous. The extra stuff here, this is just reference. We don't really need it. You can skip it. It's higher level calculus that we don't actually cover too much in this course. I'll make it more simple for you. All right, so if a function is continuous, it means we can draw on it without lifting our pencil. That's the basic definition, okay? Continuity will come up again later. So it means if it's continuous continuity, it means there's no holes, breaks, sharp peaks in the graph. If it's not continuous, we say it's discontinuous. And sometimes that comes up. So let's look at three different cases, okay? There are three cases. A graph has an infinite discontinuity if when we try to draw it, it suddenly jumps up to like a billion and has a break. Look, if I zoom in on this, the function actually never touches this point. What's this point called? Do you remember what these are called if it jumps up and never quite touches? What's it called? What's the name of that special line, that dotted line that we can never touch? It has a special name. Asymptote, you got it. And so this is you'll see asymptotes called asymptotes, and it happens when we have division, when you divide by 0. Or in other words, if you divide by 0, the function goes up and explodes, and we'll talk more about that today. All you need to know is the name. It's called an infinite discontinuity. Why is it called infinite? Because it goes up to some massive value that we call infinity. You know, if you saw Toy Story, to infinity and beyond. Is that an old reference? Does anyone understand that? It just means a really, really big number that we actually can't label. It's so big. The other type of discontinuity is called a jump, and it's labeled really obviously. It's called a jump because, look, if we follow this function from the left, we get to this point here, and then there's no value, there's no y value there. It jumps suddenly from one place to the other. And if that happens, we say it's not continuous. Of course, you can't draw that function without lifting your pencil. Look, I'll go draw, 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 draw. Oh, I have to lift my pencil and start again. It's not continuous. We call that a jump continuity, is the basic name. You often see it with piecewise functions. We have a jump in the graph. Finally, removable is called removable because of this point here. And it looks like there's a hole in the graph. So you could draw on the graph. You could go, ba-ba-da-ba-doo-ba-da-ba-doo-ba-da-ba-doo. Oh, there's a hole in the graph. I need to lift my pencil and just hop over that hole and continue. So it's Buzz Lightyear. You got it. Abdulaziz, you're my man. Nicely done. The hole in the graph. So removable, another word for it is called a hole. Just put it simply like a hole, like a space, an empty space. And instead of using the word removable discontinuity, I like to use the word hole. The reason, or the cases where we see this are when we have factors that can cancel. If you can cancel factors, we often see holes at those points. So in this case, there's a hole at, well, what value would make this 0? Look at this function here on bottom, x minus 3. There's a problem if we have a 0 from that. So if x is 3, we would have 3 minus 3, which gives 0. With 0 on bottom, the function explodes. So I'm just going to make a little foreshadowing here. There's a hole at x equals 3. All right, and there's a hole when you can cancel it out. So these are our basics. There's only 3 types of discontinuities that we talk about. One is an infinite, where it jumps up to infinity, or one way goes up, one way comes down. It's like hyperbolas almost. One is a jump style, which we usually see with piecewise functions. And the third is a removable, which is when factors cancel. It makes a little hole in the graph that we can't quite touch. So now that we have our basics, let's keep going. First of all, a removable discontinuity won't show on your graphing calculator. So even if you graph it on Desmos, I'll show you this actually. I don't have Desmos ready, but I'll bring it up in a second. I'm just going to quickly graph that second function that I looked at. So let me show you this. This one here, okay? I'm going to graph that function. It's y equals x on top, x minus 3, to x minus 3. This function, when I look at it, looks okay. You'll hopefully notice that, you know, it has values at all these points. For example, this point, of course, 0, 0. This point, it has an x and y value. Look what happens when I get to 3. It's undefined. Do you see that? It says undefined. That's because even though it looks like it's continuous, and we zoom in on this 3 point, you don't see a hole there, but there is a hole. It's undefined right at that 3 value. It's hard to find. Okay, so just believe me when I say if you're dividing by 0, but it can be canceled out, and by canceled out, I mean if we're getting this case, we'll have a hole in the graph. But overall, it's not a big problem. So just getting used to the ideas. Let's do a little bit of an example here. So it says, sketch the following graphs, state any type of discontinuity, and any values not in the domain. So I'm going to keep this simple. I'm going to just tell you that you could use Desmos, of course, as always. I'm going to sketch it for you just to save time. If you graph this on Desmos, this is what you'll get. You'll get a function that looks like this. Okay, and I'm going to ask you very simple questions on this. First of all, this is x equals 2. It says state any type of discontinuity. What's the type of discontinuity? What kind of discontinuity is this? We only have 3 types. Is it an infinite, a jump, or a hole? Well, hopefully, it's what, sorry?
An infinite.
Infinite, yeah. It goes up to infinity and down to infinity. So all we need to do is say it's an infinite discontinuity. So really the word infinite is all I'm looking for. The reason it's infinite, to be very specific, is look, as we go towards this asymptote, this is going to what? Well, it's getting smaller and smaller and smaller and smaller and smaller and smaller. It's going to go down infinitely far. It's never going to touch that asymptote. It's just going to get close. So down to negative infinity. If we go from the other side, as it gets close to x equals 2, we can say it's actually called a limit. As we get closer and closer to that 2, it goes up to positive infinity. And we're going to talk about limits later. We'll see this case a lot. But the basic idea is, look, you see this asymptote? From the left, as it gets close to it, it shoots down to these like massive numbers, like huge numbers below. And same thing from the other side. Let me just quickly show you that on Desmos. And I'll stop using Desmos soon because the basics are the most important to understand. Let me just delete this. I want 2 over x minus 2. Look what this function looks like, okay? I said it's going to go to infinity. Let's just look at this. What happens here? If I follow the function, as it gets close to 2, I'm going to go follow it and see where it ends. Okay, I'm going down pretty far. These are pretty big y values. Whew, okay. Is that 2 yet? It looks like 2. It's actually going to be 2, but not exactly. It's going to be just lower than 2. It actually never touches that line. I can always get closer, and you'll see it actually isn't touching that line. This is the line x equals 2, and of course this is our function. So they're not touching, and in fact they will never touch. That y value will get smaller and smaller forever. It will never touch the axis. Or sorry, it will never touch x equals 2, so it's called a negative infinity is what it goes to. So that's what we mean when we say negative infinity. Same thing for positive infinity. It says any value is not in the domain. What's not in the domain is whatever we would be dividing by here. So look, x minus 2 would make, we want to know what value of x would make the bottom 0. You know, set this equal to 0 and see what value would break the function. And in fact, x equals 2 must not be in domain. Okay, so the idea is if the function on bottom, if the number on bottom can make the function 0 on bottom, then we have a problem. So we just say it's not in the domain. So very simple, really. Let's look at the second one. I'm going to draw it for you. It looks like this. And there's a little hole when you graph it, or I'm just telling you, there's going to be a hole here. And in fact, there's a hole at x equals 0. Why is there a hole at x equals 0? Well, direct your attention over here. This x and this x can be canceled. It's on top and bottom. It can be canceled out. So when we cancel things out, it makes a hole in the graph. It doesn't destroy the graph. It's just a little hole. So we can say there's a hole type. And another word for that is a removable discontinuity. The reason it's called removable is we've kind of removed it from the function. We've canceled it out. So we call it removable. Which value is not in the domain? So look at the denominator and tell me what value of x would make that bottom 0. Well, it's very simple. What would be our problem? It would be if x was 0. So on bottom, if we look at the bottom, it's x. If that was 0, it would blow this function up. So that would be a real issue. So we'd say x equals 0 is not in the domain. All right, this is our big idea. So first we had our infinite, second we had our whole. Third type, I can pretty much tell, I mean, this is a piecewise function. It's kind of two functions put together. It's probably going to have a jump. So I'll draw it for you. You put it on Desmos, it looks like this. I'm just making it simple. I'd only ask you to check this as like a multiple choice anyway. What's happening here? Well, there's clearly a gap. We can't draw on the function without lifting our pencil or pen. We'd have to draw part of it, and just like you saw me do, I'll show you, right? When I drew this, I had to draw part of it, and then obviously I had to lift my pencil to draw the rest. So right away, that's a jump. So it's a jump discontinuity. And this is just basic concepts. And by basic, I mean like the fundamental concepts that we're going to be talking about later. By looking at this graph, which function is not in the domain? Which is not an x value that we're allowed to have? Two looks okay. I mean, 2 would be over here, so there's definitely a y value. So it's not that. Yeah, I think you caught yourself, Ahmed. It's x equals 0 is not in the domain. Yeah, because when we look at x equals 0, it can't be x equals 0 because these are two empty holes. And look at this. When it's less than 0, it's x cubed. When it's greater than 0, it's this function. What about when it equals 0? Nothing. There's nothing. And so we're not allowed, we can't have it x equals 0. It doesn't exist. So that's the answer to that question. Okay, so I'm going to move on to the next topic. I actually find this stuff really interesting. A lot of students find it confusing in the beginning, but they learn to like it. Maybe. I can't promise you'll like it. All I can do is I'll promise to do my best to teach it to you. So those are our 3 types. Let's look at our graphical limits. So in this case, it says graphically, which means by a graph, using a graph. What is a limit? Well, it says it's the value of the function we expect as x approaches a value. So that sounds a little bit crazy. Let's make it more specific. It says, for this graph, we can approach x equals 3 from the left or right. Okay, so let's just look at this. We want to approach this line, okay? We're just saying that in this particular example, what happens to the function, what y values is it going towards as we go towards x equals 3? So it says from the left or right. So limit as it approaches x from the right. You'll notice that little plus. You see this little plus here? That means we're coming at it from the right. So look at your graph and say, hey, what's happening here? As we look at the function and go closer and closer from the right, what value is it trying to get to? This might seem like a weird exercise, and it is because you probably haven't done this before. But what value is it trying to get to? You know, if it was allowed to get to 3, which it actually isn't allowed to touch it because we're just talking about limits, what value would it touch? What value is it trying to get to there? It's 2, right? 2. It's creeping in. It's saying, hey, I'm over here now. If I was allowed, it's like someone just before they got to 2, x equals 3, they're like, no, stop. And you're like, but I'm so close. Well, no, you're not allowed to touch it. So you're probably 1.9999999 not allowed to touch 2. But you're like, I can see it. I'm clear. I'm almost touching it. I'm basically there. So we say that the limit is 2. Let me just write down the answer. I see that you don't get it, Abdulaziz. I'll explain it again. We're going to do a lot of this. Let me just get the terminology. The limit as x approaches 3 from the right of the function, we write it like this. Limit as x approaches 3 from the right of the function is 2 in this case. So let me try to clarify this. I'll do it again from the left, and you'll see if you get it. Because once you get it, it's the same for every single limit, okay? Let's read this. The limit as x approaches 3 from the left for the function is what? So let me just look at this graph. I'm just going to zoom in on this. What it's saying, sometimes they call the x h. Yes, there are times where we do h, but it's a special case. But all that matters is the horizontal numbers. We'll normally call it x, okay? So just follow me. This graph, okay? It's asking, what is the value of this function, in this case, the curve? What value is it trying to get to as we reach x equals 3? If you weren't allowed to get to x equals 3 exactly, but you're allowed to get close. Well, let's just follow my pen, okay? you're allowed to go this way, you know, we're going this way. We're getting closer and closer. We're not allowed to touch that point. Just imagine that we're not allowed to touch it. Yeah, it would be like 2.9999999, or sorry, 1.9999999. Just like the value of x would be 2.9999999. The whole point is, just imagine it this way, okay? It's like the value at 3, we can see it on the graph that it's 2. And this might seem like a silly exercise, okay? But there's a reason we do this. When x is 3, the function value is clearly 2, or it looks like it. It's like if you're standing on the right side of it. You know, if you, let me just make an example here. Let's just say you couldn't see the rest of the function, okay? Just imagine you couldn't see it. And you had to be over here. You know, you're just standing over here and you're like, what function, what value is that function at x equals 3? Well, you'd look at it and say, yeah, it goes to 2. I don't know if it's 2 on the other side of that function, but it certainly looks like 2 now. So you would say that function is trying to get to 2. And then if you had someone else on the other side, like if you're standing only on this side, and you weren't allowed to see the rest of this function, you would probably still say, hey, it's trying to get to 2. So the two sides would agree. The person on the left side thinks it's going to 2. The person on the right side also thinks it's going to 2. And so what happens is the limits are the same. Even though we were not allowed to get to x equals 3, we can still say the function value is trying to be 2. And this is a weird idea, I get that. It will become more clear as we go through this, but for now you'll just have to take it as truth for now. So it's like we're not allowed to touch that value, but we're allowed to get close to it. So the answer is the limit as x approaches 3 from the left of this function that we've been given is also 2. And if that's the case, then we can make a final statement. We can say the limit as x approaches 3. Notice I'm not saying from the left or from the right, just the limit in general. The value that we're trying to get to, or the value that this function probably has at that top point, is 2. And I'm going to do lots more examples on this, but this is the basics of what's going on here. No, that's actually a huge point. The limits sometimes are the same. Sometimes they're totally different. For example, if we had, let's just say we had a function that looked like this. You know, the left side would say, hey, I think the function is, it looks like a 5. And from the right side, that person would be like, that looks like a 2 to me. So sometimes the limits don't match at all. And so we'd say the limit doesn't exist. In fact, the limit can go to infinity, the limit can be 0, it can be all sorts of crazy stuff. I'll make it as clear as I can. But no, the limits are not always the same. One way that my teacher used to explain this to me, what a limit is, it's like if you're getting closer and closer and closer to something, but you're never allowed to actually touch it. So this, one of the examples that he used to tell me about was like if you're trying to leave a room, okay, and you can see the doorway, but someone says, you can go and leave the room, but you're only allowed to walk half the distance to the door every time. So if it's like 10 meters away, you're like, all right, I'll move 5 meters. And then you're allowed to move half the distance again. Let me draw you a picture. Let's just say we're trying to get to the door. This is where we start. This is where you started. And this is the door, okay? It's like, this is you, and you're only allowed to move half the distance every time. So you're like, all right, now I'm here. And then once you move again, you're allowed to move half. And then you're allowed to move half. And then you're allowed to move half. Then you're allowed to move half. And then half. And then half. Eventually, you're going to be so close that you're essentially there, but mathematically you are only you still have that tiny little space between you and the door. And that's what we're talking about with limits. We're getting as close as we possibly can to the value, not allowed to actually touch the value. It's just the way it is. And there's a reason for that. We're not allowed to touch it, but I'll get into that later. So Muhammad, you said, so for it to exist, they had to be the same. That's exactly right. All right, that's exactly right. Let me move on, and hopefully it'll become more and more clear. So it says numerically, in numbers, look at this. For the graph above, when x is 2.9, notice we're trying to get to 3 from the left. We're trying to get to 3 from the left. If x is 2.9, then the value is 1.997. If x is 2.99, it's 1.99997. And the closer and closer we get to 3, the closer and closer the y values become to 2, but it never becomes 2. We can clearly see, though, that it's trying to get to 2. So this would be the limit from the left. This one would be the limit from the right. It's like, what is the function doing if we look at the x value from the right side? This is from the right. We can see that when the function is 3.1, that's a little bit bigger than 3. By the way, we're talking about 3. Something on this side would be 2.9. Something on this side would be 3.1. Really, we're trying to get to 3, but we're not allowed to touch it, so we go as close as we can. When it's 3.1, it's this value, and then this value, this value, this value. You can see that both sides are agreeing. Hopefully you can see that. So they're both saying, all right, I think we're going to 2, and then you agree, you come together, and you're like, cool, the limit must be 2. If they don't agree, then the limit does not exist. So I'm probably blowing some of your minds here, but I'm doing my best not to. It says here, to approach a value means to get close, but never to the actual number. So we can get close to 3, but we can never touch it. All right. There's a few conditions here. The most important one, well, let me just read it out. The limit is this. This is our definition. The limit as a approaches some number equals the limit. But more importantly, I would say is this sentence. If the left and right-handed limits exist and are equal, then the limit exists. That's our most important piece of information. All of this stuff here really just means this, okay? That's your takeaway. Left limit, right limit, if they're the same, we have a limit. If they're not the same, we don't have a limit. Usually we have limits for continuous functions. Okay. This will get easier because most of the stuff we do is actually math-based, not theory-based. So just stick with me, okay? Maybe this will make it more clear. Determine the left and right-hand limits as x approaches 0 for the following graphs. All right, let's do 4 examples. For this graph, this is x equals 0. So we're looking at what happens as we go to that y value from the left and from the right. Let's just use your pencil or your pen. From the left, just follow the curve. What value is it trying to get to? If you could only see, I'll do the cover up again. If you could only see the left side of the function, what value is it trying to get to? Clearly 1, not 0.1, not 0.1, 1, the y value. So what we say is the limit as x approaches 0 from the left, notice this little left of our function, whatever the function is, equals 1. So that's from the left. Yeah, it's 0.99 is really where we're at. But if we get what's called infinitesimally or infinitely close, it will essentially become 1. We can say that, if we do this long enough, it's so close to 1 that it's basically 1. Let's do the same thing from the right side. From the right side, as we go down, what value is it trying to get to? Clearly 1. Clearly 1. So as we approach x from the right side, the value of the function, what's the limit? What's that y value that it's trying to get to? It's 1. And in this case, they are the same limit. Look, they're the same. And if they're the same, we can say the limit exists. So we'll say the limit as x approaches 0, no need to write down plus and minus, just the limit, the general limit, equals 1. Okay? That's because we can also note this is a continuous function. So, questions? I don't want to go any further unless we have are any questions answered here. Anybody? Either too confused or not confused enough to answer questions? No in the middle? Okay, I'll take that as a yes. Just interrupt me if you need to. I'm going to do another one. This next one, without even doing the limit, you should be able to see that it has this jump. So it's definitely got a jump discontinuity. Let's see what that means for limits. From the left, the limit as x approaches 0 from the left of this function is what? Well, all you need to do is follow along the function on the left. The line we're looking for, of course, is this 0 value in this case. If you're only standing on the left side, you're going to go up there and you're going to say, hey, the limit is 3. You're going to be super confident that the limit should actually be to get to 3. So you on the left side would say, it's clearly 3. Anyone on this side can see that. And by that, I mean, look, if you didn't know what the rest of the function looked like, you would, of course, say 3. You would have to. There would be no other choice. From the right side, though, someone on the right side would be totally disagreeing with you. On the right side, they would be 1, exactly. Good job, Abdulaziz. So we would say the limit as x approaches 0 from the right side, if you're standing on the right side saying, I can see where this is going, you would say the limit of the function would actually be 1. And then you would say, hey, wait a second. These are not the same. And so the limit does not exist. So you would say this. I'll just write it out in English the first time. Limit does not exist. And we would say the limit as x approaches 0 of this function, I just write it as D, N, E. And the reason I use those letters is because it stands for does not exist. It's just shorthand. It's much faster to write it. You can just write D, N, E and be done with it. Okay? Is it getting clearer? I hope it's getting clearer. If it's not, then I'm not doing my job properly. If you're frustrated, you know, it's okay. Everyone gets frustrated at limits in the beginning. I'd like you to try the third one. Tell me, what's the limit from the left? What's the limit from the right? And does the limit exist? Remember, in this case, we're looking at this. This is a nice, easy one, actually. Just D and E, there's no special symbols? Yeah, not really. D and E is pretty much as good as it gets for a special symbol. Yep. So we can see that this is a whole or removable. And yet you're saying 1. Is it 1 from the left and the right? I believe it is. The limit as x approaches 0 from the left of this function is 1. I can see that. From the right, same story. They're both approaching 1. You don't need to write this out every single time, just in this section. You'll get better at it as time goes on. Is 1. And so the limit exists. And we don't, notice I'm not writing anything over here, okay? There's no plus or minus. You're just saying the limit of the function. Not the limit from the left and the right. The limit of the function in general exists. And that's the more important one. That's really the one that we care about. All right, so this is how this stuff goes. I'm going to do one more. In this case, we can see that this is an infinite case. The values are jumping down to infinity, up to infinity. What's the limit? This is a tricky one, actually, but not too bad. What's the limit as we approach x equals 0 from the left here? Negative infinity. You got it, man. So it comes and it's trying to get down to 0, but it's actually going to go down, 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 down forever. We could follow that for the end of time. Until you are on your deathbed, you would still be looking for the bottom of that function because it never ends. That's what infinity means. Negative infinity. And yes, there's such thing as negative infinity because it's either a very, very small number, negative, or positive. So even though we don't know what the number infinity is, it's more of a concept, we know that it's positive or negative. And on the other side, this is positive infinity. Why is it positive infinity? Well, because it jumps up as we get closer and closer to 0. Okay, so does this limit exist? As it approaches 0, very simply put, you can just say does not exist. You can write it out in English, or you can write it out as DNE. I know what you mean, no matter what you say. DNE or the other one. Okay, so this is how we do it by graph. And if you're given the graph, life is pretty good. If you're allowed to give the answers just based on the graph. So that would be a really nice, easy multiple choice or a short answer question, something like that. Algebraically, honestly, is not that much harder. And that's what we're going to be doing for the rest of the class. But before I move on to that, are there any questions on this? Anybody else? Abdulaziz? Assuming everyone else is there hanging out. Okay. So this, I'm glad it's clear. I'm very glad it's clear because when I did limits as a student, my teacher was horrible. I'm not saying I'm the best teacher. That's not my point. My point is my teacher was so bad, I didn't know what limits were until the final exam. Because I had a tutor at the very end that tried to explain it to me. But yeah, I don't want you to be in that position. I'd rather you just understand it the first time. So I'm trying not to pass on things that happened to me to you. Okay, let's do algebraic limits. Algebraic limits are what we have to do if we don't know the graph. You know, sometimes we'll get a function that's really complicated. Maybe you don't have Desmos available, and even if you did, it would be too hard to get the limit. We'll just do it by hand. And that might sound difficult, but honestly, limits are overall very easy to do. And for those of you that are good with your basic algebra, you should have no trouble with this. So let's do it. Algebraic limits, which means by hand or no graph. It said, from the graph section, we see that getting the limits of a function is very easy. The graphs below are all, and it leaves a little blank for you. The graphs all, oops, should have took that. The graphs below are all continuous. And we know that because we could just draw on them, and we could draw them all without lifting our pencil. If they're continuous, it means that the graphs have limits. I'm just going to put a simple thing. You can just skip this part. Don't worry about what that says. It's not a big deal. For all values of a, I'll just say the limit exists. So no matter what the x value is, the limit will exist. Okay, actually, instead of skipping it, let me just do a quick one. Let me zoom in on the first one. Let's just say I wanted the limit as we approached x equals 2. Well, you just look at this, you see that this is x equals 2. You can say clearly that the limit's got to be 0. Okay, that's all I'm talking about. What about the second one? What about when it approaches -1, so over here? What's the limit there? Also 0. Or let's take a look at this one. What about when the value of the function is, I don't know, 0? What's the limit as the function goes close to 0? Well, we just look at where x is 0, and we look at the function, and because, you know, left and right are telling the same story, we can say it's 1 or 5 or whatever the scale is. I don't know if that's 1 or 5. Let me just make it clear and say that this value is 5, just so that we're all talking about the same thing. But yeah, it would also be 1, depending on how you look at this. Okay? So if it's continuous, the limit exists, and it's very easy to find. For graphs that are discontinuous, which means not continuous, it will have a function as long as we choose points that belong to the domain. So it says as long as we choose points that belong to the domain, the limit will exist. What that means is as long as we're not like dividing by 0 or something, we're going to be okay. I'm going to skip the graphs here because it's not helpful. I want to get to the more important stuff. And so don't worry too much about those graphs. They'll become clear soon. I just want to make sure you see this. This is the most important topic or the most important piece of information in the whole unit. So I'm just going to say that this is super important. Like there is nothing more important when you are looking for limits. It's the direct substitution rule. And literally all that means is if you're trying to find the limit of something as it approaches a value, the first thing you should try is just stick that value in. You know, as x approaches 0, if you want the limit, just put in x equals 0 and see what it gives you. If it gives you a number, then you know the limit. So what this is saying, it says we can use it for all functions except for roots and piecewise. We'll see that later. The limit as x approaches some value, some number, whatever number, we can just substitute the value in so that the limit will give us just literally evaluating it like it normally would. So let me show you what that means in a second. I've got one more thing to say before we do the practice problems. Note, and this is an important note, so write it down at some point. If we get limits, like we saw earlier, limits of infinity and negative infinity are okay. Like those are okay answers. We're allowed to get answers that give us infinity. I'll say that even a limit of 1 over 0 is actually okay. The problem is the problematic limits that come up later, limits that give 0 over 0 or infinity over infinity are not okay. So those are just some 3 points that I wanted to mention to you that will become more important later. But for now, just keep it in the back of your head. You can have a function that goes up to infinity. You can have a function that goes down to infinity. You can even have a function of 1 over 0, because really that's just going to be infinity. It's like 1 divided by a really, really, really small number. We'll talk about that later. But what does 0 over 0 even mean? Like you can't divide nothing by nothing. It's not possible. You can imagine dividing something by a really small number, but you can't divide nothing by nothing. And just like that, you can't divide infinity by infinity. So these are concepts, but think of this. Infinity is a massive number, the biggest number you can imagine, and even bigger. But like the infinity on top is not the same infinity as bottom, because they're kind of both just really big numbers. So we can't actually, that's not a limit. It could be anything, right? Anyway, that's getting more theoretical. Let's do some of the math. I'll come back to that stuff later. So determine the following limits using direct substitution if possible. And that's an important note. We're going to do direct substitution, which means put in the x value, see what you get, and get the answer if possible. Let's do the first one. The limit as x approaches 4 of x squared minus 7. So let's just put in the value. That gives us 4 squared minus 7. I'm going to make my pens a little smaller today. That's 16 minus 7, that's 9. Okay, done. If you're able to substitute in your x value for the limit, you know, we're just looking at this. That's too big. If you're able to do that, you substitute the x value in and you get an answer, that is your limit. You're done, okay? So let's keep going and see how many of these we can do directly. So in this case, we have the number 2. So anytime I see an x, I'm just going to put a 2 in. So these are my substitutions. That, if you work that out, it gives 4. And you can try that on your calculator. Just trust me for now, it gives 4. The limit exists. So that's the limit. That, you know, you can even write your final answer. That's 9, and that's 4. Like, these are our answers. Done. Halas, we're finished. We can move on. Let's try C. See what happens. See what happens. Ha 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 ha. You'll see, Abdulaziz, when it doesn't exist. It'll become clear. At least I think it'll become clear. We'll see. Direct substitution, e to the power of 0 minus 0 squared. This is our direct substitution. E to the power of 0 is 1. 0 squared is 0. The limit is 1. Okay. Last one. Put in 5. That's 25. 25 minus 9 is 16. Square root of 16 is 4. Okay. 3J. 3J, I don't think it's here. Maybe you put in a 2 or something. I'm not sure what you ended up with, Ahmed, but check your work. 3J, but it's 25 minus 9. So there's no negatives. Okay, so in this case, all the limits actually do exist. All right, you following me? Yeah, sorry, it's not 0. If it was 0, you'd be right. And just to make you happy, there are no imaginary numbers here. There's no such thing as the imaginary limit. So if it comes out with an imaginary number, there's no limit. Make it easy. Okay, let's do the second example. Same idea. Determining the following limits using direct substitution. Direct substitution, by the way, this means sub in x. So let's do it again. First one, this should answer your question, Ablaziz. Try putting in 0. So we have 0 outside of 0 minus 2 over 0 minus 2. We have this. What does this give us? Someone use a calculator? 0 on top, negative 2 on bottom. 0, it's not error. It's not error. You only get an error if you have a 0 on bottom. You're allowed to have nothing and divide it into pieces. It's still nothing. So 0. The limit of this one is 0. So if you have no pizza and someone says, hey, can you cut that pizza into 2 pieces, please? You're like, dude, I don't have a pizza. So you get no pizza. It's still nothing. The difference is, okay, you have a pizza. Can you cut that into 0 pieces, please? And be like, well, I have a pizza. I either have it or I don't. So it doesn't make sense anymore. Anyway, the limit does exist. Let's move on. 2. So this would be 2 squared minus 4 over 2 plus 4. And that gives us 4 squared minus 4 on top, 0 on top over 4 on bottom. It looks like it exists again. So our answer is 0. All right. You can see, hopefully, that there's a problem with these. You know, this would cause a division by 0, which is a good point to make, but we don't care about that right now. All we care about is the limits. What's the next one? Can someone tell me? What do we got here? It's putting in 2, so 2 squared minus 4. 2 minus 2. What do we have on top? We have 0 on top and 0 on bottom. So this is a problem. This is a real big problem. This is one of our special cases. This is not allowed. There's no such thing as 0 divided by 0. It's not something that we can evaluate because we can take nothing and cut it into pieces. It's still nothing. But once we have that 0 on bottom, we have problems. So we can't evaluate this with this method. We can evaluate it with other methods. So I'm just going to say it can't be evaluated using direct substitution. All right, there's a problem, and just leave it at that. I will teach you other ways of doing this, but for now, I'll say you need other methods. And I'll teach you them later, okay? Error is the same thing as does not exist. So I'll say it does not exist. All right? If it's error, if your calculator pops back an error, most times it's going to not exist. There are cases where we won't do that, but I'll make it really clear when the time comes, okay? Let's do the next one. What's the next one? 1 over x. This is 1 over -1. That's easy. The limit's -1. -1 is the limit. It looks like it would be something weird because you have that x on bottom. It makes you feel like you're going to be tricked. It's okay. Let's do the next one. Put an 8 in. 8 minus 4. Root of 8 minus 4, square root of that is just 2. Okay, it's 8 minus 4, which is 4. Square root of 4 is 2. That's fine. And then the last one, let's see. 1 over 5 minus 9, square root of 5 minus 9. Which is 1 over the root of, what's 5 minus 9? I don't know why my brain didn't do that today. We are not doing imaginary numbers in this unit. The only time we do imaginary numbers in the course is the beginning. We can't get the limit of this because limits are very much a real concept, not an imaginary number concept. And so the answer here is it doesn't exist. So hopefully you can see the difference now. The cases where we can't do direct substitution are when we have 0 over 0, infinity over infinity, which we'll see later, or we're trying to get the square root of a negative number, things like that. I'm going to give you by the end of the course, sorry, by the end of this unit, I'm going to give you a little flow chart so you can just look and say, okay, what are my steps? And I'll tell you the steps, but not until we finish this section. Okay. What values are not in the domain for the above functions? Well, I'll just quickly talk about that. Well, before I do that extension part, can someone just tell me if you need anything else explained, or is this clear so far? You need to build on it. Okay, so which values are not in the domain? Well, for A, x equals 2. X can't be 2. Why is that? Why can't x equals 2? Because if x is 2, you'd have 2 minus 2 on bottom, which gives a 0. It would break the function. All right, so set the bottom equal to 0 and solve. The bottom, x minus 2, set it to 0. What value of x would that be? It would be 2. So x can't be 2. We're not allowed to have 2. For B, what value is not in the domain? X equals -2. Once again, I'm talking about this and this. This one relates to this. What value of 2 would break, what value of x would break that function? So it cannot be -2. What about C? What value? 2. Good. X is not allowed to be 2. For D, x is not allowed to be 0 because that would break the function. For E, x can't be less than 4. That's a special case. Let me just make a note. That's a tricky one. I'm not going to deal a lot with that. And for F, this is also a challenge. I'm just going to jump through it because it's not that big a deal. X must be greater than or equal to, or sorry, greater than 9. Okay, so 9 is kind of our problem. Don't worry too much about E and F. The other ones are standards. So be more concerned with A, B, C, and D. Okay, let's do a little bit more. The way that these notes are set up, this course is pretty good overall. The notes are laid out well. The notes in this section kind of have some random stuff thrown in. So I don't know why it talks about this particular topic when it does, but let me just try and get you through it. It says, when A is not in the domain for the limit, so for example, when x equals, when we'd be dividing by 0, we can do algebra and cancel things out. Ahmed, what? Less than 9. Yeah. So we can't have these numbers is really what I'm talking about. I think that's what you caught, Ahmed. So yeah, there was something rolling around in my head about that. So if you have limits, let me just make this clear. If you take this limit here and try direct substitution, what are you going to get? Well, you get 2 minus 2 over 2 minus 2. That ends up giving you 0 over 0 form, which is not good. We need to try something else. The first thing we're going to do is algebra, which generally speaking is usually factoring, which means see what your factors are on top and bottom, see if something cancels. In this case, it does. Boom, boom. Now we have the limit as x approaches 2 of x. And hey, we can do that. That's just 2. So if direct substitution doesn't work, and this is a huge, huge point. So let me be clear. I'll stop for a second so you're all listening. The first thing you do is try direct substitution. If direct substitution doesn't work, the next thing you should do is try to factor. Cancel some stuff, see if it works then. That will also be your limit. So that we've just learned a new skill. This I'm going to skip. There's no real reason to worry about that. I'm just going to move past it. I will note this stuff. It says, if we can't fix it algebraically, if we can't factor and cancel, we probably have an asymptote. So it says here, the limit of this function, we can't factor that, but we can see graphically that as x goes to 0, we're going from the left and from the right. Even though nothing will cancel, we can see that it does have a limit. What's the limit? The limit is infinity. I need to get my stretches in. All right, maybe I could work that into my teaching strategy. The limit is infinity. So let me recap what I just said. If you can't factor it and you have this 0 on bottom, you can probably think about the graph, and the graph might help you out. In this case, let's look. It says for the limit as x approaches 0 for this function, we can see that from the left, it's going to negative infinity. From the right, it's going to positive infinity. And so the limit in this case does not exist. Okay, just in case it comes up, I wanted to mention that. It kind of comes in a random part, but I guess there's no good place to put it. It's just saying if you can't factor it, maybe there's something else sneaky going on. This is a lot of new stuff. I get that. I will say that there is only a few different types of questions that actually get asked for limits. It might seem like a lot of different questions so far, but there's only a few types. And once you do the practice, and I know you need to do the practice, once you do that practice, you should see that you get patterns and shortcuts that build up. And it makes it pretty simple. Just make sure you put time aside to do that practice. Okay, let's do some more practice. Find the following limits by simplifying algebraically, if possible. All right, let's see this. First things first, always consider if you can do it directly. So to the side here, I'm going to do the first one. Let me just write it out. I'm just going to look at this. Can I do this one? Can I do it directly? I would have -1. Make sure you put in the brackets or else it's going to break on you. -1 plus 1. That gives us 1 minus 1 on top. That gives us -1 plus 1 on bottom. That's 0 over 0. That's called indeterminate form, or in other words, impossible to do. So Abdulaziz, I think maybe you did not square. Did you write this? or something. Be really careful with those. They can sort of mess you up pretty quick. So in this case, it's 0 over 0 form. Oh, okay. Well, yeah, actually you're right. It is 0, it is -2. So this is 0 over 0 form, which is why we need to factor. But it's almost always easier to do direct substitution first, is kind of my point. So let's do it. The first one, you got to keep the limit. I'm going to be pretty picky about this. Until you do a substitution, you have to keep the limit there. So the top, this is a difference of squares. So hopefully you know that for difference of squares, you set up two brackets, one's plus, one's minus, square root of the first one, square root of the second one. Okay. Square root of this one goes here and here. Square root of this one goes here and here. Difference of squares, x plus 1, and then bam, bam, those cancel. We can do our limit now. Let's put -1 in, -1 minus 1. This is our substitution of our limit. -1 minus 1 is -2, so Abdelaziz's got it 100%. Bring out those big guns on the assignment and you'll have no troubles, okay? So if you can see it's going to factor, that's a great thing. It means that it has a hole, which means that you'll have a removable discontinuity. It's a hole, and it probably has a limit. Let's do the next one. The next one's a little bit tricky, but I'm not worried. Let's see if we can handle it. I'm going to do the simplification on the side here. So 3 plus h, we need to square that. We need to expand that out. That's the same as 3 plus h, 3 plus h. So our regular method, multiply these together, multiply these together, multiply these together, multiply these together. 9 plus 6h plus h squared is what you'll get. Okay, so let me write that out. We still need the limit as x approaches 0. Sorry, I want to use better marker. The limit as x approaches 0 of 9 plus 6h plus h squared minus 9 over h. Just in case you got lost as to what I'm doing here. Oops, wow, that's very ugly. Sorry about that. That's the same thing, and now we can simplify and see what happens. X minus 1. Which one are you talking about, Ahmed? The x minus 1 part. Oh, yeah, I see. Sorry. Okay, let's simplify this. We've got 9 and a -9. They'll cancel. Nice and easy. 9 and a -9 will cancel. Let's see what else I can do. I can factor out the h. So the h can come outside. You might be wondering, how do I know to factor all this stuff? And the answer is factor everything you can whenever you can. Because with limits, the ones I'm going to give you almost always will cancel to something. That's the whole point. I'm trying to get you to see that even though it looks like it can't be done directly, you can probably cancel something out and then it can be done. So cancel those h's, and now I'm going to do the limit. So 6 plus, as h goes to 0, so 6 plus 0. The limit is 6. The limit of this is 6. Even though we have this weird h going on, the limit is 6. Let me quickly show you a graph to remind you that all of this stuff is actually talking about things that are happening on graphs, even if we can't see it. So our function, I'm just going to put it in terms of x's. Oops. So our function is same as 3 plus x squared minus 9 over x. Look at that function. That's a whole lot simpler function than you might have thought it was going to be. If we zoom in on this, as x approaches 0, or in this case h, but it all means the same thing, as we go to 0, what are we going to get? 6. It goes to 6, so we're correct. And look, if we actually look and see what that function is at that point, undefined. You see that? So even though it goes to 6, the limit is going to 6. It looks like it's going to be 6. There's still a hole there. We can just find the limit. We just can't fix the hole. Anyway, the graph confirmed that we're nailing it. Or should I say Abdulaziz is nailing it. No one else is really answering. Well, Ahmed's answering, so we shouldn't put you down. Okay, let's try C. Someone tell me what the answer for C is going to be. Take 1 minute. See if you can get it. Hint. You're going to factor, and you're going to cancel. I know that because if you put in 3 directly, you're going to get 0 over 0 form. 4. Anyone else have any answers? Any ideas? I agree with you that it's 4. I agree. X plus 1 equals 4. Let's see. The limit as x approaches 3. You always need to write that limit. Until you've substituted in or found the limit in some other way, you have to keep writing that limit in front. Because it's not just the function, it's the limit of the function. We factor the top. Hopefully you can handle that. What two numbers multiply to make 3 and add to make 2? Well, we only have 2 choices, really. We have 1 times 3. It can either be a plus 1 times negative 3 or a negative 1 times positive 3. And definitely for this case, it's going to be this guy. Wait, it's going to be this one. So now we've got our trusty cancellation. The limits are very satisfying when you know how to do them, because you're like, hey, it factors and they cancel and I just substitute and I got my answer. Really, is that all? And the answer is, yeah, it is all. That is all you have to do. So a lot of students end up liking this topic the most because they find it simple. But of course, it depends on the student. I'm going to put in the substitution. I'll put in my 4. Wait, 3. And we indeed get our 4. Okay, so I have 20 more minutes left. I want to cover as much as I can without any delay. I'll do one more of these. Do you want to do D, E, or F? You know, the other ones will just be homework or extra practice later. You can try D. I have a feeling that Abdulaziz already did D, which is why he wants me to do that one, a little break. But let's see. Let's do D. The top. I can see why you wanted to do this one. This one factors differently. This one I'm going to just say that I wouldn't normally give. You'd have to split it up a little bit. You'd have to split the middle number. I can go through how to do it if you want. Let me just... I'll go through it. Okay, I'll go through it. So what we need to do, we need to deal with the top. And the tricky thing is, this is a trinomial, a 3-piece equation, but it doesn't factor easily. And again, this is a special case, but because you wanted me to do it, I'll do it, of course. We have 2x squared minus 3x minus 2. And I'll just quickly remind you how to do this. You have to take the middle piece and you have to split it up. And by split it up, you need to make it, you need to take this piece here. You need to rewrite it so that it can be factored with the whole expression. What I mean by that is you need to be able to now factor this piece and then factor this piece. And it's kind of annoying actually, but we need to factor just the blue part. So what's the common factor here? You need experience to be able to do this, which is why I won't actually go through it that slowly. The common factor is definitely 2, and there's an x as well. So if you factor out 2x from those first 2 terms, you end up with x minus 2. And what's left is x minus 2. So the blue stuff factored, the purple stuff factored, and now we actually need to factor out the whole x plus 2, because this piece here and this piece here are actually common to both terms. We put a 4. All right, so let me try to make this as clear as I can. Sorry, bud. Just look at the purple, or that middle number. I knew ahead of time that I needed to make something that could factor out to be x minus 2. There's rules for this, but honestly, I'm not going to go through all of them because this doesn't come up very much in this course. I just knew ahead of time I needed to be able to factor it. So I turned the 3x into a negative 4x and a 4. Look at this. Negative 4x plus x is negative 3x. So I'm allowed to split it up so that it'll allow me to factor it. But again, let's not waste too much time on it. We'll end up bogged down on something that I'm probably never going to ask you in this course. It's like a question that just got thrown in the middle, weirdly complicated for no good reason. So when I finish factoring this, I'm going to factor out that x minus 2. I factor out x minus 2. That will cancel out this and leave the 2x. And it'll factor out this and leave a 1. So it looks like this. Many students won't remember how to do that, and honestly, it's okay. I'm not going to make you do real complicated factoring. It's just not going to happen. So let me rewrite the top. And then the bottom. And once we have it in that form, we can cancel things. The x minus 2's can cancel, and we can do our direct substitution. That's 4 plus 1, which is 5. So that's a tricky one. There are kind of standardized ways to do that factoring. I am trying to remember the easiest way to do it because I haven't taught that factoring in a long time. I only know it the way that I do it in my head, and it's not that helpful. So do you want me to, between now and next class, find you the easiest method to do factoring like that? So I don't mind summarizing it for you in a real simple way. Abdulaziz, you still with me? Okay. Do you want me to summarize it for you in an easier way for next class, or are you okay now? No. That's probably the only one we're really going to see, actually. I don't know why it ended up there. I think it's a challenge. Okay. So E and F are easier. They're more like the types we had before. The E, the only hint I'll give is that you need to factor the top and you need to factor the bottom, but the rest is really simple. And for F, you just factor the top. And the rest works out the same, okay? So I'm gonna keep working. For 2, you can sketch, you can just use Desmos. Don't worry too much about 2, just use Desmos and look at your limits. We did one like those today already, so I'm gonna move past it. Sorry, I keep burping, I'm very, very sorry. I wanna get to the more interesting stuff. 3 is a question that sometimes comes up on a test or a quiz, so I'm gonna do it quickly. It just says that we have a piecewise function. It's broken up into 2 pieces. And it's saying, what happens as x equals 0, as x goes to 0? Well, it's saying from the left, as we go towards x equals 0, it gives this. So what happens is, if we put in the number 0.01 into this function, for example, from the left is this side, if you put negative 0.01 in your calculator, you'll get 0. I think 99. Let me just double check. I did this earlier. Yeah, 0.99, which means you're coming to 0 from the left. Remember this. You're going from the left. But we're doing it numerically, which means we're taking numbers. So what's a number that's close to 0? Well, negative 0.1. What's a closer number to 0? Negative 0.01. What's a number even closer? Negative 0.001. That actually gives 0.999. And if you keep going, it gives 0.9999. What is that number? Well, for all intents and purposes, it's approximately 1. It's essentially 1. So as we go closer and closer to 0, it's going to be 1. So by the graph, we see that that's true. But by the numbers, it's actually true. And you can put those numbers in. You know, put these into the calculator. You'll see if you put this into this formula, you'll see that that works out. If you put it into this formula, which means we're going to go from the right, if you put in 1 to that formula, you get 1 minus 1, which is 0. You put 0.1 in, you get negative 0.9. You keep going, just trust me on this. I could give you the table is probably what I would do if I get asked this question. Just follow the pattern. So from the right, we can see we're trying to get closer and closer and closer and closer and closer to 0. We're not allowed to touch 0, so we get as close as we can. What number is that? What is that number essentially? Is it 1? No, it's negative 1. Negative 0.9999999 is essentially negative 1. So we can see that for this function, therefore, the limit as x approaches 0 of this function does not exist. Okay, so these graphical ones, don't get, overwhelmed by them. Just look at the table and say, okay, as the x value gets closer and closer to where we want it to be, so closer and closer to 0 from the left in this case here, it gets closer and closer to 1. As we look on the other graph, as we get closer and closer to 0 from the right, it becomes negative 1. Why do I not put 0.11? Well, because, let me try and make this as clear as I can now. Let's just say we have the point 0, okay? We've got 0. And we're saying, okay, let's get close to it. So this is our value 0.1. What if we went even closer, like divided that by 10? Take 0.01, divide it by 10, you're 10 times closer at 0.01. And if we go 10 times closer than that, we get 0.001. And if we go 10 times closer than that, we get 0.0001, but we never actually get to 0. Do you see what I mean by this? I'm just trying to get 10 times closer every time. You could even put 0.00000000001 into this formula, and it'll be that minus 1, and you get the same results. The idea is that I'm trying to get close to 0, but not exactly 0. That's the big idea here. You see what I mean, Ahmed? Yes. Yeah. You're saying, 0.1, we're trying to get to 0, not 1, right? So we want to get smaller than 0.1. Just keep putting in smaller numbers. But in the smallest possible number you can think of that's close to 0. Okay. So just to answer your question, look at what's highlighted, okay? When x is greater than 0, so on the right side, this is our function. We need to take these values and put it in for x. See what we get. So 1 minus 1 gives us 0. 0.1 minus 1 gives us negative 0.9, and so on. We're just putting those numbers in as the x value and getting back the y value. And those are the numbers that come out of it. Okay. Sorry about that one. That's a little bit tricky, but take some time to think about it. There's a practice question in the practice section on that, and you should be okay. Inshallah. All right. Let me see this. I didn't get as far as I wanted to. Just seeing, let me just check one thing, because I know you have an assignment coming up. I don't want to get deep into something that you can't finish today. Let me see. We have, okay. I will finish off this topic tomorrow, because I wanted to start it today. It doesn't look like I'm going to start it today. I'll say, I'm just going to give you a slight introduction to it, and we'll end off, okay? And then you can go and do your assignment. The last thing I'll say today is that something special happens when we have cases like this. Okay? So let's just say we were trying to get close to the number 0, but not equal to 0. So we can't do this by direct substitution, but let's just consider it as limits. Imagine we're going to 0, okay? What's a very, very small number that is close to 0 but not quite 0? Well, you could say 0.1, or you could say 0.00001, just like we did, or 0.000001. Basically what we're saying is that we have 1 over some small number, small positive number. Okay? That's what it means. Instead of putting in 0, think about what would happen if you divided by a tiny number. So just take your calculator. This is the last thing I'll ask you to do. Take 1 and divide it by a really, really tiny number. So put it in like 0.00001. Okay? So imagine it being something like that. Like put in the number 0.0001, or you can put as many zeros as you want, and press enter. You get a big number back. For example, if I put in 0.0001, I get back like 100,000 or 10,000, depending on how many zeros you have. If you put in 0.0000000001, which is extremely close to 0, you get an even bigger number. So what happens is when we divide by tiny numbers, if the x is on bottom, it goes to infinity. Okay, that's the story here. That's our final case. If it was a negative number on bottom, it would go to negative infinity. But I'll cover that again tomorrow. I don't want to muddy up the explanation too much. Sorry I didn't get to everything I wanted to get to, but c'est la vie. Is there any last minute questions on any of this topic before you go ahead and try your assignment? No. Okay, c'est bon. I'll see you all tomorrow. I hope you have a good assignment. If you have any technical issues or anything, let me know. I'll turn off the recording now. Bye-bye.